Section: Introduction. In this section, we explore how large language models can be enhanced to understand and utilize information from significantly longer pieces of text, up to 128,000 tokens in length. This capability opens up new possibilities for these models, such as answering questions from multiple documents, understanding code on a repository level, modeling long conversations, and even powering autonomous agents that use language. A key challenge in testing these models' ability to handle long texts is the needle in a haystack test. This test involves finding and accurately reciting a specific sentence hidden within a much larger document. Despite the theoretical support for handling 100,000 tokens by some open-source projects, they struggle with this test, unlike advanced, proprietary models like GPT-4128K, which excel at it. Our goal is to refine the training process of language models so they can successfully navigate the needle in a haystack test with 128,000 tokens of context. Considering that most models are initially trained on much shorter texts, up to 4,000 tokens, and the computational demands of processing longer texts, this might seem an ambitious goal. However, we demonstrate that it's achievable with resources typical of academic settings. We focus on two versions of the Llama 2 model, with 7 billion and 13 billion parameters, making minor adjustments to their architecture and concentrating on optimizing the mix and amount of training data to enhance their performance on long context tasks. We propose that the ability to process information from any part of a long text is largely developed during the initial training phase, even when that training involves much shorter texts. This stands in contrast to approaches that rely on extensive additional training with huge amounts of data to improve long text handling, which can be as resource-intensive as training a model from scratch. Our approach shows that with a relatively modest increase in training data focused on longer texts, between 1 and 5 billion tokens, we can significantly improve a model's ability to work with long contexts. An important aspect of our strategy is how we increase the amount of long text data in the training mix. Unlike previous efforts that simply added more long text data from specific domains, such as books, we maintain the original proportion of data from different domains and increase the representation of long texts within each domain. This method avoids the performance issues in other domains that can arise from an unbalanced focus on long texts. Our results indicate that this balanced approach to data enhancement allows our models to perform better on long context tasks without sacrificing their ability to handle shorter texts. In summary, we present a specific strategy for improving the ability of language models to handle very long texts, up to 128,000 tokens, by continuing their training on a carefully selected mix of data. This approach has enabled our Llama 2 models to approach the performance of leading proprietary models on challenging tests like the needle in a haystack, suggesting that effective long context modeling is within reach for projects with academic-level resources. In the background section, we delve into the recent advancements in language models that can process extremely long texts, highlighting the emergence of new applications and the importance of the needle in a haystack benchmark for evaluating these models. Despite the challenges, our work advances the capabilities of open-source models in handling long texts and narrows the performance gap with top-tier models like GPT-4, setting the stage for further exploration of long context modeling within the constraints of academic budgets. Section Summary. In this section, we explore the significance of utilizing a context window of 128K tokens for large language models, enabling them to excel in tasks like multi-document question answering and long history dialogue modeling. We focus on enhancing language models' ability to handle long context tasks by proposing a data recipe involving continual pretraining on 1 to 5B tokens of per source length upsampled data, which has shown promising results in improving long context performance. Our approach aims to bridge the gap between existing models and frontier models like GPT-4128K on challenging benchmarks like the needle in a haystack test, paving the way for further advancements in long context modeling within academic constraints. Section: Long context data composition. In this section, we discuss how we continue the pre-training process using a dataset known as Slim Pajama. This dataset is essentially a recreation of the Llama pre-training data mix, which is made up of a variety of sources. 82% of the data comes from the web, with 67% from Common Crawl and 15% from C4, 4.5% from code on GitHub, another 4.5% from Wikipedia, 4.5% from books, 2.5% from archive, and 2% from Stack Exchange. The composition of Slim Pajama is very similar to the original Llama dataset, which helps us avoid issues related to changes in the type of data the model is exposed to during further training. This similarity has made Slim Pajama a popular choice for many recent studies. We've noticed that the length of documents and their sources are intertwined challenges in preparing our data. For instance, books and GitHub code tend to provide the longest documents, followed by archive papers, while web pages and Stack Exchange posts are usually shorter. If we were to increase the representation of longer documents in our dataset, it would inadvertently shift the balance of content types, such as increasing the proportion of book content if we upsampled documents longer than 100,000 characters. To address this, we've adopted a step-by-step approach to separate these two factors, as illustrated in one of our figures. We've explored several strategies, including cutting documents into 4,000 character chunks, which maintains the original mix of content types but breaks up longer documents, potentially losing some long-range coherence. Another strategy is cutting at 128,000 characters, which keeps more of the document's original structure but doesn't address the imbalance in document lengths across different sources. We've also tried upsampling documents by their source, which maintains the original mix while increasing the representation of longer documents, and global upsampling, which increases the representation of longer documents regardless of their source but can slightly alter the content mix. Additionally, we've specifically upscaled documents from archive, books, and GitHub, assuming these sources are more likely to have longer documents. Our experiments have shown that simply cutting documents at 128,000 characters isn't enough for tasks that require understanding longer contexts. Upsampling longer documents seems necessary, but improving performance in one type of content doesn't always translate to others, indicating the need for a balanced approach to content mix. For the engineering part, we've continued pre-training with a focus on per-source upsampling, training models with 80,000 character sequences for our 7 billion parameter models and 64,000 for our 13 billion parameter models. Despite the seemingly daunting task of training with such long sequences due to the quadratic complexity of attention mechanisms, we've found it to be feasible. Most of the training time is actually spent on data transfer operations, which are not affected by sequence length in the same way. As a result, training with 80,000 character sequences is only 3 times slower than with 4,000 character sequences. Our setup is notably more cost-effective than previous efforts that trained on larger datasets. However, we've reached the limits of what's possible with the Hugging Face Deep Speed framework in terms of context length, as attempting to go beyond our current setup leads to memory issues. We use a constant learning rate of 2e-5 and have adjusted the base of our positional encoding to better suit longer sequences. We pack data into 80,000 character chunks, a common practice, and set our batch size to 4 million tokens. This batch size is consistent with what we'd use for shorter sequences, as we're increasing the length of each chunk but reducing the number of chunks per batch. We train on 5 billion tokens, which equates to 2,000 optimization steps given our batch size. Section Summary. In this section, we explore the composition of long context data by utilizing the Slim Pajama dataset for continual pre-training, which closely resembles the data used for pre-training Llama models. We analyze the relationship between document lengths and their source domains, highlighting that books and GitHub code are the longest sources, while web pages like C4 and Stack Exchange tend to be shorter. Different methods such as cutting at 4K, 128K, per source upsampling, and global upsampling are considered to balance the domain mixture and length distribution for optimal performance in handling long context data. Section: Experimental Results. In this section, we delve into the experimental outcomes of our study. We've further trained the foundational Llama 2 models, which have capacities of 7 billion and 13 billion parameters, using a dataset created through our per-source upsampling strategy. This dataset comprises 5 billion training tokens. Initially, we demonstrate that our approach surpasses notable open-source benchmarks such as Yarn Mistral with 7 billion parameters and 128K context length, and Long LORA with 7 billion parameters and 100K context length. Interestingly, our method narrows the performance gap with the more advanced GPT-4 Turbo with 128K context length. Following this, we dissect the components of our data preparation strategy. We explore the concept of data sufficiency, particularly focusing on the impact of scaling the dataset from 100 million to 1 billion tokens. This scaling enables our model to more accurately retrieve information from any location within documents of 128K tokens in length. We then examine the mixture of data sources, especially the importance of upsampling longer sequences. Our findings suggest that the original data mixture used by Slim Pajama, despite having about 30% of its data longer than 4K tokens, is not adequate. Upsampling longer sequences is crucial for the model to effectively handle long contexts. However, we also observe that improvements in one domain, such as books, may not fully transfer to others and could potentially have negative effects. Specifically, enhancements in the books and code domains show that gains in one can adversely affect the other. Traditionally, validation loss has been the primary metric for evaluating models. However, we argue that relying solely on validation loss is insufficient. Two models with similar validation losses can exhibit vastly different capabilities in retrieving information. This is illustrated in our figures. To assess our model's performance comprehensively, we employ a real-world, book-length question-answering benchmark, which is more challenging than earlier benchmarks due to its focus on longer contexts of 128K tokens. When comparing our method against other leading long-context language models, such as Together AI's Llama 2 with 32K context length and LMSE's LongChat v1.5 with 32K context length, our approach shows superior performance. We attribute the underperformance of some models to insufficient pre-training or a lack of diverse training data. Our method not only enhances precise information retrieval but also maintains robust performance in shorter contexts, as evidenced by strong scores on the MMLU benchmark, a widely recognized measure of a language model's general capabilities. In terms of data quantity, we hypothesize that the ability to retrieve information accurately over long contexts is inherently developed through extensive pre-training, even if the pre-training contexts are much shorter. Our experiments support this hypothesis, showing that with gradual increases in the amount of data used for continual pre-training, the model's ability to retrieve information improves significantly. Notably, after pre-training on 5 billion tokens, the model performs well within a 0 to 80K token range and can generalize to contexts up to 128K tokens in length. The process of continually pre-training our Llama 2 model with 7 billion parameters is both time and cost efficient, requiring only about 5 days on a setup with 8 A100 GPS with 80 GB each. This efficiency opens up new possibilities for future research into fine-tuning and reasoning over long contexts, areas that have seen limited exploration in open-source projects. Our findings also suggest that long-context continual pre-training might be effectively pursued as a distinct phase following pre-training focused on specialized capabilities like mathematics and coding. Section Summary. In this section, we present experimental results showcasing the effectiveness of our pre-training strategy on large-scale language models. We demonstrate superior performance compared to existing baselines like Yarn Mistral and Long LORA, and highlight the importance of data quantity and mixture in enhancing the model's ability to retrieve information accurately within long contexts. Our findings suggest that continual pre-training with a moderate amount of data can significantly improve the model's retrieval capabilities within long-range contexts, offering a cost-effective approach for future research in long-context language modeling. Section: Data Mixture. In this section, we delve into the reasons behind the necessity of per-source length upsampling when we're mixing data from different sources. We maintain the original mixture ratio of the data sources, which for our project, Slim Pajama, includes 67% from Common Crawl, 15% from C4, and smaller percentages from GitHub, Wikipedia, Books, Archive, and Stack Exchange. Within each domain, we increase the proportion of sequences longer than 4,000 tokens from about 30% to about 70%. This adjustment allows us to keep the domain mixture ratio constant while only altering the length distribution of the training documents. In contrast, if we were to upsample long sequences globally without considering their domain, or specifically target long sequences from code, books, or archive, we would end up changing both the domain mixture and the length distribution. We evaluate all the data mixtures against a baseline, which is the original data packed to either 80,000 or 64,000 tokens for the continual pre-training of the 7 billion or 13 billion parameter Llama 2 models. This baseline approach essentially maintains the original data as is, including the naturally occurring long sequences that would otherwise have been cut to 4,000 tokens. If a data mixture strategy is effective, it should outperform this baseline, do-nothing, approach. Our findings show that for short context data, 0-4,000 tokens, most data mixtures negatively impact web pages from sources like C4, Common Crawl, and Stack Exchange, with the exception of the per-source approach. We also note that performance improvements in one domain, such as books, may not necessarily transfer to others and could even detrimentally affect code performance. The per-source length upsampling emerges as the most balanced approach, enhancing performance for contexts between 4,000 and 128,000 tokens without significantly compromising short context performance, unlike other methods that exhibit trade-offs across different domains. Based on these observations, we advocate for the per-source length upsampling strategy. This strategy's key distinction from the original data mixture lies in the distribution of sequence lengths, as it maintains the domain mixture ratio while increasing the presence of tokens from longer sequences. We further illustrate this by comparing two Llama 2 7 billion models trained with either the original or the per-source upsampled data mixture, focusing on their per-length validation loss and needle in a haystack performance. Our results not only demonstrate why we outperform the long LORA, which uses the original data mixture without length upsampling, but also highlight the importance of precise retrieval capabilities, a factor that mere test loss evaluation might overlook. In our discussion, we attribute our advancements over existing open-source baselines to meticulous data engineering. This underscores the growing recognition of data engineering's critical role in large language model research, on par with modeling and algorithmic innovations. We also highlight the significance of certain data details for achieving strong long context performance, which could be easily missed. Our work benefits from the latest breakthroughs in machine learning systems, especially flash attention, which significantly reduces memory usage in the attention mechanism. Looking ahead, exploring sequence parallelism could potentially enable the training of models capable of handling even longer contexts, such as 200,000 tokens. The transformer model's reliance on position embeddings poses challenges for generalizing beyond trained contexts, suggesting the need for some continual pre-training. Recent work on RNN-like architectures, which inherently encode positional information, shows promise for zero-shot generalization to longer contexts, a hypothesis worth testing with the needle in a haystack benchmark. Research in long context language models, particularly at the 100,000 token scale, is still evolving. Our study focuses on continual pre-training, with limited exploration into instruction fine-tuning for tasks requiring understanding of long contexts, such as repo-level code comprehension. We hope our findings lay the groundwork for future research into supervised fine-tuning for long context language models at the 100,000 token level.